Hi all. In this video, we will discuss about the ModN synchronous counters. Okay, in the last video, we have learned the synchronous up counter, down counter, up down counter like that. So here we are going to learn ModN counters, that is shortened modulus counters. That is shortened modulus means we know that. Using a 3-bit counter, that is using 3 flip-flops, we can count from 000 to 111. So total 8 counts are possible. That is 8 states are possible there. That is 000 to 111. Okay. So we can call it as a mod 8 counter. Mod 8 counter. But suppose if we are asked to design a synchronous mod 6 counter. So for this 6 states also we have to use 3 flip-flops, because based on the relation capital N less than or equal to 2 raised to n, here capital N modulus is 6, mod value is 6, and it should be less than or equal to 2 raised to n. Then the value of small n will be 3. Okay, so we have to use 3 flip-flops. So using these 3 flip-flops, actually we can count from 000 to up to 111, but here we need to count only 6, that is from 000 to 101. 6 counts, 0, that is 1 2 3 4 5 6 counts, that is 000 to 101. Okay, so this is a shortened modulus counter. Okay, that is mod 6 counter. And here the states, the another state after when this 101, it will again start from 000 to 001 like that. So here 110 and 111 are the invalid states here. Okay, invalid states. So so for this shortened modulus counter, in the second last lecture I have discussed about the lockdown condition. Okay, locked condition. So that is when this one of these invalid states, okay, due to some any disturbances or noises, when this invalid state comes at the output of our flip-flops, okay, then what will happen? Sometimes this will when the condition is 110, when the output is 110, so sometimes after next clock pulse, it will again move from the used invalid state 111 like that. Okay, so there is an lockout condition will be there. Okay, lockout condition will be there, so we can discuss it later. And also the state diagram is like that. And here this is the excitation, required excitation, and this is the present state and next state. So we are starting from 000, then next one is 001. Okay, next state is 001, then from if it is 001, then next state will be 010. If it is 101, next state will be 000. Okay, so based on these values we are writing the required excitations by considering Q3 and Q3. Okay, present state is 0 and next state is 0. Okay, so we can design J3 and K3 based on this value. When 0 condition are there, we know that the excitation from the excitation table of JK flip-flop, we know that for the condition 0 it will be 0x, for 0 0x, again it is 0 0x, again it is 1, which means 1x, then 1 x0 1 0 x1, like that we can write all J2 K2 J1 K1 like that. Okay, so here also this J1 and K1, all the values are 1s or x. Okay, no zeros are there. So from this value itself you can say that the value of J1 and K1 will be it is equal to 1. Okay, so here this is the corresponding K-map for J3 K3 J2 K2 and J1 K1. Okay, and the value of J3 we will obtain like that, Q2 Q1. Okay, it should be very careful. Okay, there is a chance for a false entry in the corresponding cells, so very careful when you are entering these values, J3 and K3 values in the corresponding cells. Okay, and here the K3 is Q1, J2 is Q3 bar Q1, and K2 is Q1, and J1 is 1 and K1 is 1. Okay, and based on these values we are constructing our circuit. Okay, J1 is 1, K1 is 1, this is 1. Okay, and J2 we know that it is Q3 bar Q1, so Q3 bar here taking from here, and Q1, and K2 is Q1, K2 is Q1, like that we are drawing the circuit. And next we have to check for the lockout condition. Okay, lockout condition, that is whether our counter is self-starting or not. That is, when any one of the invalid state comes at the output of the flip-flops due to any disturbances or noises, we want to know that whether it will again come back to its valid state or not. Okay, so for that, first we are considering the first invalid state, that the present state it as 110. Okay, we are considering it as 110, first invalid state. Okay, and we know that here Q1 is 1 and Q1 is 0, Q1 is 0, and Q2 is 1, and here the Q3 is 1. Okay, Q3 is 1, and at the present condition we have to find the present inputs at all these flip-flops. Okay, and first we are looking for the first flip-flop. We know that at any time the J1 and K1 will be on, so J1 and K1 will be on, and we have to look for J2 and K2. What will be the value of J2 at this condition? Okay, so we know that Q1 is 0, so the output of the AND gate should be 0. Okay, so J2 will be 0, and what about K2? K2 is also 0 here. Okay, so K2 will be 0. And what about J3 and K3? And you know that Q2 is 1, and the another input of AND gate is coming from here, that is Q1. We know that it is 0, so 0 here, 0 comes here, and the output of the AND gate will be 0, so J3 will be 0, and also K3 is given as the Q1. Okay, Q1 will be K3, so K3 is also 0, so J3 K3 is 0. Okay, and using these values, using these present input values, we can determine what will be the next state of the flip-flops. So the current state is 0, 1, 1, that is 110 condition. Okay, Q3 is 1, Q2 is 1, and Q1 is 0, this condition. And using these inputs, okay, after the next clock pulse, using this input, what may be the next output of these flip-flops? Okay, and first we can move from here, that is J1 is 1, K1 is 1. Okay, and the present value of Q1 is 0. Okay, and we know that when J1 is 1, K1 is 1, the toggle condition based on the truth table of JK flow, toggle condition is there, so this Q1 will change to 1. Okay, so here you can see that Q1 is 0 here, Q1 is changed to 1. Okay, and next J2 and K2 is 0, 0. Okay, so when J2 and K2 are 0, both inputs are 0, we know that no change condition is there for the flip-flop. So Q2, currently Q2 is 1, so it will continue it as 1. Okay, so here Q2 is 1, Q2 is 1, and again J3 and K3 is 0, 0, again the no change condition is there, so Q3 is 1, so it will continue it as 1. Okay, so the next state will be 1, 1, 1. Okay, so this is another invalid state. Okay, and also we are again checking for this 1, 1, 1 condition, that is present state is 1, 1, 1. Okay, then what will be here Q1 is 1, Q2 is 1, and Q3 is 1. Okay, then what will be the corresponding inputs? In the last case, same as the last case, we are going to find the corresponding present inputs. Okay, so J1 and K1 is 1. So here J1 and K1 is 1. And what will be J2 and K2? And here Q1 is 1. Okay, the another input is coming from Q3 bar. Okay, in the previous, here the Q3 is 0. So Q3 bar will be 0. Sorry, here the Q3 is 1. So Q3 bar will be 0. So here 0 comes here. So J2 will be 0. Okay, and what will be K2? K2 is same as our Q1. So here the Q1 is 1. So K2 will be 1. So J2 and K2 will be 0 and 1. Okay, next we will go for J3 and K3. So here it is J3 and K3. Okay, J3. So here the Q2 is 1 and another input is came from Q1. Q1 is also 1. So J3 will be 1. J3 will be 1. Okay, so 1 1. The output of AND gate will be 1. So J3 will be 1, and also we know that K3 is same as our Q1. So K3 will be 1. So this is the present inputs. So based on these present inputs, we have to find the next output. After the next clock pulse, what should be the output of the flip flop? Okay. So here we can start from here. That is J1 and K1 is equal to 1. J1 is K1 is 1, and Q1 is 1 here. Okay. So the toggle condition is there. So the output will change from 1 to 0. So Q1 becomes 0. Okay. And again J2 is 0, K2 is 1. J2 is 0, K2 is 1. When J2 is 0 and K2 is 1, we know that whatever may be the previous condition, always the output will be 0. That is Q2 will be 0. So Q2 will be 0. And J3 and K3 will be 1 1 again. That is toggle condition. So here Q3 is 1. So toggle the output will toggle. So the Q3 becomes 0. So the next state will be 0 0 0, which is a valid state for a mod 6 counter. That is, which means when any of the invalid state comes, after the first clock pulse, if an invalid state 110 comes, after the first clock pulse it will move to 111, and after the next clock pulse it will move to 0 0 0. So naturally, if you are applying a clock pulse, our counter will restart from 0 0 0. Okay, naturally it will come to 0 0 0. So it is a self-starting counter. Okay, we don't need to add additional combination circuits for the working of our synchronous mode 6 counter here. So it is a self-starting counter, because if any of the invalid state comes, naturally it will come to a valid state 0 0 0. Okay, so likewise we can discuss about the synchronous BCD counter, which means mode 10 counter. It is also called decade counter. Okay, so here capital N is 10. So 10 less than or equal to 2 raised to 4. So number of flip flops n, small n will be 4. So we have to use 4 flip flops here. And also we know that using these 4 flip flops we can count from 0 0 0 0 to 1 1 1 1. Okay, so only we are considering only 10 states. It is because it is a mode 10 counter. It is a BCD counter. So it counts from 0 0 0 0 to 1 0 0 1. 10 counts will be there. After this 1 0 0 1, all other states are treated as invalid state. That is 1 0 1 0, 1 0 1 1, like that up to 1 1 1 1, all are considered as an invalid state. Okay, so here also we are considering JK flip flop, and this is the conditions, present state, and this is the next state. Okay, our present state 0 0 0 0, next state will be 0 0 0 1. Okay, like that we are writing this table, and base rows is Q4 and Q4. We will write the excitation values for J4 and K4, and using Q3 and Q3 we will write J3 and K3. Using this Q2 and Q2 we will write the excitation for J2 and K2 and J1 and K1, like that. Okay, so this is the corresponding the clear excitation table, and this is the corresponding K maps for J4 K4, J3 K3, J2 and K2, J1 K1, like that. Okay, and this is the circuit we obtain. Okay, and here again we are going to check for lockout. Okay, and we are considering that the present state it has a 1010, which is the first invalid state. 1010, that is a value of 10. Okay, 110 is 10. When 1010, we have to find the values of J4 K4, like that. Okay, so here the Q1 is 0 and Q2 Q2 is 1 and Q3 is 0 and Q4 is 1. Q4 is 1. Okay. And we know that for this corresponding output, what will be the corresponding inputs for all the flip-flops? This J1 and K1 will be 1 always. This J1 and K1 will be done. And what will be J2 and K2? So here Q1 is 0. So the output of the AND gate will be 0. So K2 will be 0. And also this J2 will be 0. And also this K2 will be 0. So J2 and K2 will be 0. First condition. And what about J3 and K3? So here Q2 is 1. And another input of the AND gate is coming from here, that is Q1. So the output of the AND gate will be 0. Here Q1 is 0. So the output of the AND gate will be 0. And the same input is given as the input to the K3. So J3 and K3 will be 0, 0. And what happens to J4 and K4? J4 and K4. Here Q3 is 0. So J4 will be 0. And K4, it is Q1 here. So Q1 is 0 here. So K4 also will be 0. So J4, K4 will be 0. So here is corresponding present inputs, and we want to find the next state based on these inputs. Okay, so when J1 and K1 is equal to 1, our Q1 is currently Q1 is 0. So the toggle condition is there. So Q1 changes from 0 to 1. So Q1 will be 1. Okay, and also J2, K2 and K2 is 0, 0. So for 0, 0, no change condition is there. Whatever may be the output here, it will continue it as like this. That is Q2 is 1 here, so it will continue it as 1. So Q2 will be 1. Okay, and J3 and K3 is also 0, 0. So the output Q3 is continued as 0. So here Q3 is 0. And J4, K4 is also 0, 0 here. So the output of Q4 is continued as Q4 is 1 here. So the output Q4 it is continued as 1. Okay, so the next state will be 1, 0, 1, 1. Okay, and nextly in the next condition we are considering this 1, 0, 1, 1 as the present state, 1, 0, 1 as the present state, and we obtain it as the next state. Same as in the previous case, we obtain it as the next state will be 0, 1, 0, 0. 0, 1, 0, 0 is a valid state for a mod 10 counter. That is 0, 1, 0, 0 for denotes for 4. Okay, so 4 is a valid state here. So we understand that when these two invalid state comes, that is for 10, 1, 0, 1, 1, 0 is 10 and 1, 0, 1, 1 is 11. Okay, when these two states come, when it is 10, it will in next state it will change to 11. 1, 0, 1, 1 is 11. So 10 changes to 11 and this 11 changes to 4. So 11 changes to 4. So automatically the counter starts from this 4. Okay, that is counter enters into a valid state. Okay, so we can call it as a self-starting. Okay, self-starting condition. And also other invalid states are there. So for 1, 1, 0, 0, we know that the next state is 1, 1, 0, 1, and for 1, 1, 0, 1 the next state is 0, 1, 0, 0. That is 1, 1, 0, 0 means 12 and 1, 1, 0, 1 means 13. So when an invalid state 12 comes, after the next clock pulse it changes to 13, and again after the next clock pulse it again changes to 4, which is an valid state for our counter. Okay, and for other condition 1, 1, 1, 0, next state is 1, 1, 1, 1, and for 1, 1, 1, 1 the next state is 0, 0, 0, 0. That is 1, 1, 0, 1, 1, 1, 1, 1, 0 means 14, 1, 1, 1, 1 means 15. So after next clock plus 14 becomes 15, and after again next clock plus this 15 becomes 0, which is a valid state for our counter. So for all invalid states, okay, when any of the invalid state automatically comes at the output of these flip-flops due to any noises and disturbances, automatically our counter will reach to a valid state. So we can call this counter also as a self-starting counter. So mod 10 counter, that is BCD counter, is a self-starting counter. So thank you. I hope you understand the mod N counter well. Thank you.